All right, y'all. Happy Friday. What a feeling. 1 week and 1 day left together. Wow. 1 week and 2 days we got to find. So, a couple things I want to note to you all. One, I just texted the TA asking about the grading, so if he responds before the end of class, I'll let you know. Again, he should be done in the next few days, but we'll see. Other than that, student perception of instructor, really appreciate if you all do that for me, makes my heart happy. And I don't know if there's too much more to say. Oh, I extended your all's quiz. So the one that was due tomorrow on rotational stuff, I extended that to Wednesday because we didn't finish this last Monday. So as promised, I did extend that one. Potentially, I will extend the next one as well, but nothing too crazy. I know it's going to extend this to Wednesday after that. So we'll see. All right. Yeah, I feel like there was one other thing. Oh, yeah, the joke. All right. What do y'all call a pickle waiting in line? A cucumber. It's queued up in line. Yeah. I don't know what a cumber is, though, so I don't know how that works. But, yeah, so last class, y'all, we talked about rotational kinetic energy, which was the energy is really rotated. And it was 1/2 I omega squared. You can see it on the board. And we gave a problem where I said, hey, I got two spheres. Sphere 1 is half the radius of sphere 2. If you have half the radius, you have 1/4 the rotational energy, according to this. Assuming you're spinning at the same rate. Now, the reality is you have two objects rolling down a hill. And you say you have two cylinders rolling down the hill. And you said, which one's going to get to the bottom first? What's kind of interesting is the radius seems to kind of cancel out. So, yeah, that's just a kind of fun fact. Because if you all replace them, whatever. I don't want you all to get confused with that. If the radius is halved and everything else is the same, the energy is according. Yeah. Oh, yeah. So, a lot of people, if you made a mistake here, you probably picked D, and that's because this problem is flipped from what you all are normally used to. Normally, I say, what's the new one in terms of the original one? What's 2 in terms of 1? This one's 1 in terms of 2. So, sphere 1 has half the radius. And notice that all these answers are in terms of sphere. How does the kinetic energy of 1 compared to the kinetic energy of 2? So sphere 1 is half the radius of sphere 2. We use sphere 2 as the reference, because that's what it's getting referenced. Is it 1/4 the second? Is it 1/2 the second? Is it twice the second? Or is it 4 times the second? And to that end, it is 1/2 the second, or 1/4 the second. You could flip it, though, and you can see the answer up top. You can see the other way to express this answer. That the second one has 4 times the kinetic energy of the first one. It's the exact opposite. Just rearranging the equation. So, if this answer is what you get, you just need to know, oh, okay, just divide 4 to the other side, and you got the other answer. So that works as well. Okay, so we talked about that. Let's see. What else did we go over last time? Wow, we really didn't make. I did an integral problem with you all. Gave you a foreshadowing of your future. Good to kind of look through, think about, and yeah. So today we're just going to continue on with this, and we might very likely finish everything. We'll see. If we don't finish, we're going to get real close, which will mean everything else is just review. So we'll see what happens. All right. What's cool is this problem here is all the numbers are reasonable, are accurate. So I have a neutron star. That's a star that's super dense, like the densest, other than a black hole, I suppose. The densest star, it's not a black hole. It has a mass of 2 times 10 to the 30 kilograms. It has a radius of 10 kilometers, which you may think is big, but for a star, that's real small. So we have a mass of 2 times 10 to the 30 kilograms. We have a radius of 10 kilometers. We'll go ahead and convert that, 10 E3 meters. And it has a period, and the symbol for period is capital T, of 0.02 seconds. And it says, what is the rotational kinetic energy? All right, so rotational kinetic energy, it's 1/2 I omega squared. That's the original equation. You don't have I currently, and we don't have angular frequency currently. So I'm going to let you all think about it and see how would you get I, how would you get angular frequency. See if y'all can figure it out. Given what I have, how can I get I? Given what I have, how can I get omega? We have everything I've written all the givens you need. Well, yeah, I've written all the givens you need. I have done that. There's no secret givens hidden here. So ironically, I think the simpler one is I. We have something rotating, so you just ask yourself, what shape is this? Well, hopefully you know it's a sphere. If not, that's okay. But a neutron star is a sphere, like every single star that's out there. So then you say, what's the moment of inertia for a sphere? Again, in a problem, if I gave you a problem like this on the quiz, I would give it to you in the problem. It'd be very kind. But we've seen this one a few times now, so I actually have it memorized. 2/5 mr squared. Talk to me in a month and I'm sure I won't have it memorized anymore. 2/5 mr squared. So that's really easy. We got M, we got R, easy peasy. We'll just plug that in a second. Give you all a few more moments. How am I going to get angular frequency from what I have? That's the one to see how much more you remember. Purity. We haven't seen that in a while. Let's go ahead and pull up the formula sheet, y'all, because this is what you'll have access to on the test. So you would have to know that period is capital T. You can't really use the formula sheet very much if you don't have that. All right, hunt it down. It is right here. Now, you can honestly come up with this yourself. It is fairly useful to know that period and frequency are the exact opposites. Period is how long it takes for one revolution. Frequency is how many revolutions in 1 second. They're the exact opposite of each other. They're exactly flipped. Period is revolutions or seconds per revolution. Frequency is revolutions per second. Literally just flip the units. So frequency and period are related by, they're the inverse of each other. So frequency equals 1 over period, and vice versa. Period is 1 over frequency. We don't want frequency though. So then we remember that frequency. So omega is 2 pi f, and so subsequently omega over 2 pi. Let me be super careful here because I don't want to do anything silly. So frequency equals omega over 2 pi. Yeah, we're kosher. Omega over 2 pi. All right, and you've got period, so just rearrange things.
The recitation scale, my TA shows omega equals velocity over radius.
Yep.
How do we get that?
Oh, that was one I gave y'all. Remember all of the, so theta, actually, distance, so how far something, the arc length, is r times theta. Velocity is r times omega. Acceleration is r times alpha. You want to go from rotational to linear, you just multiply it by r. That's also, so that's kind of one of the ones I give you all. That is the relationship between linear and rotational variables. So you can see that.
And we don't use it?
Nope, don't need it. Because you don't have the velocity. We don't have the velocity in this problem. What we have is the period.
You can't find it, the period in
You could, but it's another way. You could potentially, yeah. If you know the period, you know the time it takes. If you get the circumference of a circle, 2 pi r, you get the same thing. Yeah, you could totally do that as well. Yeah, you could do 2 pi r over period, and that'll give you the velocity, and then you can do things. All right, so yeah, I mean, nothing really to say at this point, y'all. I don't even, I guess we can calculate it just to see how ridiculous of a number it is. It's going to be a lot. Like, this thing has more rotational energy than anything in the universe. Of all the spinning objects in the universe, this has the most. So it's just going to be a matter of putting the numbers in at this point. Nothing special, nothing fancy. I'll chuck them in there. We'll plug it in just because it will be an interestingly, ridiculously large number. So let's just see how ridiculously large this number is. And it's always good practice to plug things in. All right, so kinetic rotational energy equals 1/2 times 2/5 times 2e30, which is it's a lot of mass. The mass of the Earth is to the 24, I believe. So this thing's got more mass than the Earth does. Makes sense. It's a neutron star. Star's got a lot more mass than the Earth does. 10e3 squared times 2 pi over 0.02 squared. That's a heck of a lot of numbers, y'all. Let's see what we get. 0.5 times 2 divided by 5 times 2e30 times 10e3 squared times parentheses 2 pi divided by 0.02 squared. And then I double check that what I wrote down is what I intended to write down. All right. This is a stupid number. 3.95 times 10 to the 42 joules. Such a stupidly large number, you can't, not even in the realm of possibility of imagining how much energy that thing has. These things rotate so quickly that little bumps on them are going inside it so quickly that they end up emitting, I think, X-rays and stuff like that. Like, these things have stupid energy. Neutron stars do. Yeah, so that's a 3 with 42 decimal, again, just wild. But it's a reality. This isn't made up. These are real numbers. And it is as simple. These things are basically perfect spheres. So, and they spin. Cool. All right. So again, I've been kind of pushing this again and again and again and again and again. If you understand linear motion, force, acceleration, position, velocity, time, F equals ma, torque, or not torque, F equals ma, P equals mv, momentum, all that stuff, if you understand all that, you just got to swap in the rotational variables and you get the new equations. So, let's see if you know them. What is the rotational analog for F? So F is what we use for linear motion. What's kind of the equivalent for rotational motion? Is it F? Is it tau, which stands for torque? That's lowercase Greek letter, tau, T-A-U. P for momentum or rotational kinetic energy. What is the rotational analog for F? So F, a force, makes something accelerate. Which of the following on this board makes something have angular acceleration? A force makes an object accelerate. Which of these makes something experience a angular acceleration? That's the connection here, y'all. What makes something start spinning faster, slower? Oh, look at that. You all know it. All right, we'll go to 1 minute and 5 seconds. It's either you know it or you don't kind of situation. In 5, 4, 3, 2, 1. So what's the rotational analog for F? What makes something start to, if it's not rotating, what makes it start rotating? If it is rotating, what slows it down? A torque. A torque makes something. When you apply a force at some radius, so that's my radius, that's my force. Remember, y'all, torque is R cross F. R, F, sine theta. It makes something rotate. All right, great, awesome. Oh no, is it a ghost? It's a ghost. Let's see, is it as bad as I think? Yep. All right, so I'm going to show you all this, and then I'm going to close the thing and restart it because that's the only way. What is the rotational analog for M? What is the rotational analog for M? I wish I could freeze this thing, but I can't really start it because I got to restart my whole program. It got angry with me. We've had so long without ghosts. But they're back. I hate the ghosts. Goodbye, ghost. All right, so what is the rotational analog for mass? Mass is the quality of an object, where if you have more mass, it's harder to get it accelerating. What is the equivalent for rotational? What is the quality of an object that makes it harder to rotate? Harder to speed it up / slow it down. Boom, boom. Give you all 30 seconds. Because you've had so much quality time to think about this. Is it M? Is it F? Is it capital I? Or is it KR? M is mass, F is force, I is moment of inertia. K is kinetic rotational energy. And we'll close this out in 5, 4, 3, 2, 1. All right, y'all did great. You best believe it's moment of inertia. How the mass is distributed. The closer it is to the center, the easier it is to speed that thing up or slow it down. Very nice. All right, so we take all this together. Hey, I've got a rotation analog for M. Hey, I've got a rotation analog for F, which means we can make a new Newton's second law, but for rotation. Remember, F equals ma? So just replace it. F equals ma, replace F with torque, replace M with I, replace A with alpha. Ta-da! You all just made Newton's second law, but for rotational stuff. Torque equals I alpha. And this is extremely useful. So this is when I mentioned torque way back when, like that was last week or something. This is why torque is useful. It explains why things start spinning faster or start spinning slower. The more torque you can put on something, the more angular acceleration you can get. So electric cars can put a lot of torque out, and so they can accelerate their wheels. They can get a lot of angular acceleration on their wheels, and that lets them be really fast. So torque is very useful. It lets you get that angular acceleration. Some other applications of high torque is if you're towing something, your vehicle needs a lot of torque because you're fighting. So remember, you're not the only thing acting on the object, especially when you're trying to move a big old truck. To get that wheel to spin, you are fighting all that resting mass and all the friction and things like that to get it moving. You need a lot of torque to be able to get enough angular acceleration to make it happen. So, very, very, very useful thing. This explains why anything rotates. Yeah?
Torque is also a vector, and you have to decompose everything into components.
Yeah, torque is also a vector. What's nice is you're only going to have one of two directions, into the page or out of the page. Yep, so the nice thing with this one is I'm not going to give you a torque that's like two-dimensional, because I don't even know, that'd be wild. Like, I've never even seen a problem with a torque that had two dimensions to it. In general, something can either rotate clockwise or counterclockwise, and that's kind of it. You never have something like also spinning, but technically it could. Yeah.
So we don't need to worry about breaking everything.
No, you just need to worry about, and we'll actually see this in the next slide, if whether or not the torques are in the same direction or opposite directions. If they're in the same direction, add them. If they're opposite directions, subtract them. So it is a very nice segue. The unit for torque is just newtons times meters, which is kind of nifty. Because torque, we've already seen torque. It was FR. Okay, so let's apply this. Let's actually do the exact thing your classmate mentioned. How do we fit, torque is a vector, which means it has direction, which means we have to determine whether or not they add or subtract. This is a picture of a car. Well, this car broke. I had this thing. It was a fun toy. My 2-year-old daughter would chase it around, and then she'd say, "I did it," when she'd pick it up, and it was adorable. It broke. But it is a cool toy. And the way this toy worked is it had wheels on both sides, and the remote control, so it had 2 joysticks. One of them went up, down, the other one also went up, down. So you can make the left side go forward and backwards, and you can make the right side go forward and backwards. So if you want to go in a straight line, you push them both forward. You want to go backwards, you push them backwards. You want to go left, you have to put one forward, one backwards. Whatever. It's a good torque example. So, if I hit the joystick forwards here, well, okay, I guess it's reverse. If I hit the joystick backwards on one of mine, and the joystick forwards on the other one, what will this thing do? Will it go backwards, forwards? Will it spin clockwise, or will it spin counterclockwise? This is a torque problem. Which way will its angular acceleration be? And you can kind of predict it, even without knowing anything about physics, but we'll talk about the, what's going on here. Oh yeah, you can't answer it, because I didn't open it. All right, I'll give you all like 40 seconds to think about it. I have high hopes for this. And to draw what's going on here, we have some radius. We have a force going that way. We have a force going that way with another radius. Yeah.
The arrows are backwards, right? Like reverse?
Yeah, so the back of it is on the top of the picture, and the front of it is that. So yeah, backwards. So A would mean, does the car go this way? That would be backwards. B is go forwards. Spin clockwise would mean that the car goes this way. Or spin counterclockwise means the car goes that way. I don't know why I put the back on the top of the picture. Well, I just took the picture and it was what it was. All right, so we'll go for 5 more seconds. 5, 4, 3, 2, 1. All right, and again, you all can get the answer to this probably without me having taught you jack squat. If I'd asked you this first day of class, you probably would have gotten it right. Because you've seen this stuff in your life. So what's the answer? Let's go through it the more complicated way. Let's practice some right-hand rule. All right, y'all. So this R vector goes this way. The force is that way. What is the direction of torque for the left wheels? Which way is the direction of torque? So remember, y'all, it's R cross F. So you point your fingers in the direction of R, and you swing them towards F. So you point your fingers in the direction of R. I can't really swing my fingers that way. So you rotate your hand. This one makes a torque into the page. So on the left side, we get a torque in. Torque in. Awesome. Great. Let's look at the other side. We have a force that's going down. We have our R. We kind of extend it. So we extend our R to make it easier. You put your fingers in the direction of R, you swing them towards F. Oh, look, we get another torque in. They line up with each other. Why does this matter? If the direction of torque is into the page, if the direction of torque is into the page, your fingers show you which way it's going to angular accelerate, i.e. which way it's going to start to rotate, which is clockwise. And again, you could kind of figure this out other ways, but I wanted to kind of use the tools that I've also been teaching you all. To that end, let's go ahead and do a slightly more complicated version. All right. Same situation, but I have an arrow. The arrow on the left side is bigger. The force that this wheel is outputting is bigger, and the force that this wheel is outputting on the right side is smaller, and they're pointed in the same direction. So which way will this thing go? Option A, will it go backwards and curve right? Or will it go backwards and curve left? Or will it spin in place clockwise? Or will it spin in place counterclockwise? What will this car do? And I'm still fairly optimistic you all can predict what it's going to do. Well, that's interesting. No, it's still pretty good. Not as good as the last one, but still pretty good. All right, I'll close this one out at 120. Then we'll close this one out in 5, 4, 3, 2, 1. All right, so what's it going to do? I'm going to again do it the more complicated way, because intuitively, if you can figure it out intuitively, then you don't really need too much. All right, so same thing, y'all. We got an R vector for that one. We got an R vector for that one. This one, the left side, is still into the page. I still get a torque into the page. The other side, I get a torque out of the page. But this guy wins. More force, more torque. So I'm going to get a torque that is predominantly that way. Now this other one is going to be doing some stuff, so yeah, it's going to try to make a clockwise rotation, but it will get some forward momentum as well. An extension of this problem is what would happen. So there's a couple pieces at play here, y'all. This tells you that the car is going to want to rotate clockwise. And so that may lead you to if you do this just pure mathematically, this tells you that you're going to rotate clockwise. But that is not the answer, because we also draw a free body diagram. And I have forces. I have a force going up and another force going up. So which way will my thing accelerate? Normal acceleration. A will be up. Alpha will be clockwise. You have both. The world is complicated, y'all. And not only do things rotate, they also move linearly. So you have to sometimes do both a free body diagram and torque. What a fun time. All right. So, but for now, let's just focus on torque. So here's a problem that's a bit more involved, a bit more classic. A pulley of moment of inertia, 2 kilograms meter squared, is mounted on a wall as shown in the figure. Light string, that's very important. We're going to assume these strings have no mass. If they had mass, oh gosh, it's not very fun. I'll talk about why. What are the angular acceleration of the pulley? What is the linear acceleration of the weights? Assume that R1, and that may be a little hard to see. So let me go ahead and clarify that. This is R1. This is R2. Oh my gosh, did I ghost? This is mass 1, this is mass 2. Yet again, I have the pleasure of closing it, restarting it. Otherwise, any bit of writing I do won't get saved, and it'll carry on to every other. Oh, it's the worst. I hate it. PowerPoint's being cruel to me today. But start thinking about how you'd solve this, y'all. It won't take that long to reopen it. So I got a pulley with 2 masses pulling on it. Are they contributing torque in the same direction or opposite directions? That's a really important question here. And that'll be pretty easy to answer once we look at it again. All right, and we are back. See, look. Oh, haven't gotten to that one yet. All right, so there's that. This is gray. This is mass 1, this is mass 2. All right, let's just write what's given. We have R1 is 50 centimeters, that's 0.5 centimeter, or 0.5 meters. R2 is 20 centimeters, that's 0.2 centimeters. Mass 1 is 1 kilogram, mass 2 is 2 kilograms, and we have our moment of inertia of 2. I'll make some room and shove that in there as well. And we have I equals 2 kg dot m squared. All right, we are solving for alpha and A. And you know what? I'm going to be so kind. I'm going to go ahead and tell you all we're going to use torque equals I alpha. I just taught it to you, so that's the assumption. All right, think about it, y'all. How are you going to do this? I'll give you that for now, see if y'all can figure out the next step. We want alpha, we have I, so really the question is, how do you get torque? See if y'all can figure it out. How can we get the torque? And we got two different torques too, I'll even tell you that. Alright, so a week or so ago, well actually let's just jump over to the formula sheet again. Where's torque?
Is it air shallow?
Yeah, did you find? Yeah. Sorry, I should have let you do it. Yeah, it's that one. RF sine theta. All right. Torque equals RF sine theta. All right. Well, we don't have F. I'll let y'all think about that. What force is causing these things to pull on the thing? Because that's not given either. This thing won't work in space. I mean, why is it going to rotate? Because the force of gravity is m times g. Now, what is the angle? So this is where the force is acting. The force is downwards. The radius vector is that way. So what's the angle between those? 90 degrees. So theta is 90, which means it's 1. All right, so it's going to be fairly straightforward at this point, y'all. We'll find each torque. Won't be too bad. We're going to need more space, though. And so something that's interesting here, you may be like, what would be an example, like where would this even show up? A really common example of this is elevators. Elevators, obviously they're used to pull you up. They have pulleys at the top. Why does that matter? They have something called a counterweight. The counterweight is the exact mass of the elevator with no one in it. So an elevator would have potentially something like this, where one of these is maybe the elevator, and one of them is the counterweight, and the purpose of the counterweight, it really comes down to, when no one's in the elevator, you don't want to really have to make the thing work too hard for it. So you have a counteracting torque that makes it so that it counteracts the torque that the elevator is literally pulling down on the pulley with. So we got two torques. Torque 1, that is going to be R1 times M1 times G. And then we have torque 2, which is going to be R2 times M2 times G. Boom, boom. Get those. Easy peasy. 0.5 times 1 times 9.8. 0.2 times 2 times 9.8. Probably an interesting question here would have been which one would have generated more torque if I hadn't, like, without doing any math. It's the one that's farther away because it's the ratio of the distance is bigger than the ratio of the masses. So that's just an interesting thing to think about. Remember, the farther away you are, the farther away you are, the more torque you can output. So this is going to be 4.9, and the units for that are Nm. And then the other one is going to be 3.92. All right. Awesome. I got two torques. These are vectors. You all need to decide whether we're going to add them or subtract them. Which one's positive? Which one's negative? Are they both positive? Are they both negative? Think about it. Decide. Are these going to help each other or are they going to oppose each other? That's the question. And again, we'll do it vector-wise, but we'll also just kind of do it intuitively-wise. So, torque 1. Torque 1 is this guy. R cross F. That torque is out of the page. R is here, F is down here, R cross F, you get a torque out of the page. That one's going to cause the thing to rotate counterclockwise, like you expect. The other one, F is down, R is to the right. Right hand rule, stick your fingers to the right, swing them down, you get a torque into the page. At this point, I tend to say out of the page is positive and into the page is negative. So if I get my net torque, it's going to be T torque 1 plus negative torque 2. Why are we getting net torque? Because if we want to find the angular acceleration, we need net torque. Just like if you all want to find the total acceleration, you need a net force. Like the free body diagrams from way back when. You have multiple things acting on it. We got to figure out what the sum of them is. They're coupled. So you get 4.9 minus 3.92, which comes out to 0.98. I'll double check myself because, again, anytime you're overconfident, you tend to make mistakes. All right. Awesome. And it's positive, which means this torque is out of the page. That tells us that this thing's going to rotate that way. But we're not done. We got one last step, y'all. This problem did not say find net torque. This is all a means to an end. This problem said find the angular acceleration. So, torque equals I alpha, plug and chug, 0.98 is going to equal 2 times alpha. Alpha is just going to equal 4.49 rads per second squared. Few steps, but if you know what you're doing, each step is pretty small. This is just a net force problem. Hey, find all the forces acting on it. This is analogous. This is analogous to a net force problem. Hey, find the acceleration of a car that experiences this much friction and has this much applied force. Okay, do I add or subtract them? Set it equal to M and A, divide by the mass, get the acceleration. This is just like one of those problems. We just had an extra step of finding, we had to kind of calculate the torque. All right. Now we're not quite done. There's one more step. It says find the acceleration. I have not shown you how to, I have not put that on the board yet. I'll give you all 30 seconds to see if you can figure it out. What is the acceleration of each object? They will each have a different acceleration. That's a hint to you. Find the acceleration due to each object. Here's a formula sheet. See if you can find it. We are trying to find the acceleration given all the other crap that we have. There it is, y'all. The relationship between angular acceleration and tangential acceleration, just multiply by r. Easy. So I'm not going to even work that out. I'll write it out, but A equals R alpha. A1 equals R1 times alpha. A2 equals R2 times alpha. You'll just put in the numbers. They each will accelerate differently, which is very interesting. The rotational acceleration of this object is the same everywhere on the radius. But remember, y'all, the outside of that drum has to go a farther distance in the same amount of time. The nice little meter stick. When a meter stick spins in a circle, the outside literally has to travel a farther distance in the same amount of time. So the outside has to accelerate quicker. The inside has to accelerate not as quick to get the same result. So, there you go. Good things. This is good for you all. Rotational stuff is, I don't know, I think it's super interesting. I think it's really cool because there's not much new at this point we're just connecting things that kind of already learned. Yes, there is some new variables and things like that, but if you can just make the connection to things you've already learned, then it's not too bad. It's just something with a new paint job. To that end, let's continue practicing our ability to find the analogies. If P equals mv, what do you think the equation is going to be? So P is regular momentum. What do you think the equation is for angular momentum? Swap in the analogous variables, y'all. What is the rotational equivalent to mass? What is the rotational equivalent to velocity? Just swap them in, and you got your equation for angular momentum. So is angular momentum going to be m times omega? Is angular momentum going to be I times omega? Is angular momentum going to be I times v? Or is angular momentum going to be m times omega times v? See if y'all remember what the variables represent as well, because that is a skill in and of itself. Oh, and look at that, y'all. The end is almost in sight. Yeah, y'all are doing pretty good with this. Alright, we'll go to 105. Close this out in 5, 4, 3, 2, 1. So angular momentum is just like P, but for rotation. What's the equivalent for m? Moment of inertia. What's the equivalent for velocity? Angular velocity. Boom, you all just came up with the equation for angular momentum. Yay! There it is in all its glory. What is angular momentum? So it's the rotational analog of linear momentum. Remember I had a hand-wavy definition for regular momentum that said how hard it was to stop something or get something to start moving. So the rotational analog for angular momentum, how hard it is to stop a spinning object or get an object to start spinning. It's not exactly a scientific definition, but it gives you a good intuition. If something has a lot of angular momentum, it's hard to stop spinning. If it has a lot of angular momentum, it's going to be hard to, it's kind of the main one. Why? Because it's going to be spinning really fast. Or it's going to have a lot of moment of inertia. That's what a flywheel is. A flywheel is a big hunk of metal that you get spinning really fast. It's got a lot of mass and it's usually a decent sized radius. So a flywheel has a lot of moment of inertia and you get it spinning really fast, and those things are incredibly dangerous once they get going. Because if that thing pops off, whatever's spinning it, it's not going to just stop spinning. That thing's going to fly off in whatever direction, and it's a giant hunk of mass spinning super fast. That hits you and can kill you easily. So flywheels, they're used in various devices to kind of store energy, smooth out things, smooth out the motion of stuff. You don't need to know what a flywheel is, but you'll see them at some point. They're really, really useful. They're in all sorts of applications. All right, onwards and upwards. A solid sphere and a hollow sphere have the same mass and radius, and they are rotating with the same angular velocity. Which one has the higher angular momentum? Is it the solid sphere, the hollow sphere? Both have the same angular momentum and possible to determine. What's very important here, what's very, very important, they have the same mass and the same radius. People's intuition, when they think of a hollow sphere, they think it's lighter. Not in this case. They have the same mass and the same radius. I want to make certain you all don't choose this based on, oh, a hollow sphere. That's easy to stop. Maybe it is. But in this case, if that solid sphere weighs 100 kilograms, the hollow sphere weighs 100 kilograms. They weigh the same weight. They have the same mass. So what's different? How the mass is distributed. The only thing that's different between a solid sphere and a hollow sphere in this problem is how is the mass distributed. Everything else is the same. So, based on that. Ooh, this is good. We're splitting thirds right now. People are between A, B, and C. Which one has the higher angular momentum? We shall see. I'll give you all 10 more seconds. We'll go to 35. We'll close this out in 5, 4, 3, 2, 1. And again, if people got this wrong, it's because they thought the hollow sphere had less mass. Traditionally, it does. But in this case, I had some wild situation. Maybe the solid sphere is made of plastic and the hollow sphere is made of metal. Whatever. All that matters, what's my equation for angular momentum? I omega. Alright, so I compare the two. I've got I of a hollow sphere. Let's actually find these. So they both have the same omega. That's the same. So we're going to scroll. And actually, you all didn't need to have these memorized. So I will show you what they are, and I'll tell you why one is bigger than the other. We go back to our nice little table of moment of inertias. And we look right here on the right side. I zoom in so it's easier to see. A hollow shell has a higher moment of inertia. Why? Because the mass is farther away. Remember, y'all, moment of inertia is all about how the mass is distributed. The farther away it is from the radius, the harder it is to spin. The farther away, in a hollow shell, you've kind of put it all on the outside. So more of it is farther away. So I'll put the numbers down back in the thing so we can just compare them. So, hollow, solid. The hollow sphere has an angular momentum of 2/3 mr squared. The solid sphere is 2/5 mr squared. 2/3 is bigger than 2/5. 2/3 is 0.66666666. 2/5 is 0.4. So which one has more? The hollow sphere. Given the same mass and the same radius and the same angular velocity, that one wins. So, be careful, y'all, because you're going to encounter things in life that don't, like, yeah, sure, generally hollow things have less mass, but in this problem it didn't. So, very important that you kind of always go through the steps. Think through it logically. There's a reason equation exists. Intuition is useful, but it's always good to check it against the math. All right, y'all, we'll finish this up. Look, the end is nigh. 5 more slides of this class, and then it's all just reviewing. The end is so close, y'all. How many is going to be teaching you all? Then you got the final. That's also close. Oh, final week, 47 questions. It's official. 47 questions. Took me about 20 minutes, 30 minutes to get through. So you should have more than enough time.
Can we have more?
Can you have more? Yeah, you're welcome to come up with your own problems. 47 fit really nicely on 4 pages. So y'all will have 2 pages front and back, and then a blank sheet of paper, and then the Scantron.